morning, friends. This is Sumit Chandok. In today's lecture, we will discuss about inner product space. So, first of all, we discuss about the motivation behind the inner product space. In a nonlinear space, we can add vectors and multiply vectors by scalars, just as in elementary vector algebra. Furthermore, the norm on such a space generalizes the elementary concept of the length of a vector. However, what is still missing in a general norm space, and what we like to have if possible, is an analog of the familiar dot product A dot B and modulus of A, which is equal to B square root of A dot A, and condition of orthogonality, that is A dot B is equal to B 0, which are important tool in many applications. Hence, the question arises whether the dot product and orthogonality can be generalized to arbitrary vector spaces. In fact, this can be done and leads to inner product spaces. And complete inner product spaces are called Hilbert spaces. Inner product spaces are special norm spaces. In the real case, an inner product is a symmetric bilinear form and positive definite on V cross V to R, where V is a vector space. In the complex case, it is a Hermitian symmetric conjugate bilinear and positive definite on V cross V to C. A semi-inner product gives rise to a semi-norm, or a inner product gives rise to a norm. Thus, an inner product space is a particular case of a normed linear space. Unless otherwise is stated explicitly, all the Hilbert spaces mentioned are assumed to be complex Hilbert spaces, whose definition is simple to state. A complete inner product space with a norm that is derived from the inner product. Hilbert spaces are special Banach spaces. Further, because of the inner product structure, Hilbert spaces have extra features than Banach spaces, which can make them more special and hence lead to several interesting properties. For example, some ideas for use in differential equations like Fourier series or Fourier analysis do not fit well in a Banach space setting, but fits very well in a Hilbert space setting. So first of all, we define what is a inner product space. So let V be a linear or vector space over a field F, and field F may be a complex or real, by an inner product or pre-Hilbert space on a vector space V. We mean a mapping F defined from V cross V to F that assigns for each uv belongs to V cross V a value in F denoted by this, called a scalar valued expression, or simply inner product of u and v. So inner product of u and v is being represented by this sign, such that for each u, v and w belongs to a vector space V and lambda belongs to field F, we have inner product of a u comma v is equal to be conjugate of inner product of v comma u. This is also known as a Hermitian or conjugate symmetric. Number two, inner product of a lambda times u v is equal to be lambda times uv, lambda times inner product of a uv, and inner product of a u comma v plus w is equal to be inner product of a u comma v plus inner product of a v comma w. This property is known as additivity. Now we're going to be the fourth property is the Inner product of a u comma v is greater than or equal to 0, and inner product of a u comma u is equal to 0 implies that u is equal to 0. Now we will discuss about some of the properties, some of the discussion over these properties. So there are a number of observations that can be made about these axioms. The fact that the inner product uv must be real follows from the property 1 on taking v is equal to be u in a 1. And further, for lambda is equal to 0 shows that the inner product of 0 comma v is equal to 0 for every v belongs to be v. And in particular, we have u is equal to be 0 implies u inner product of a u comma v is equal to be 0. So further in the next section, we will discuss about the norm defined over the inner product, and which is being defined as a norm of a u is equal to be the inner product of a u comma u makes v into a norm space. A vector space V together with its inner product, here this is said to be an inner product space. And inner product space is also called a pre-Hilbert space. As in the case of a norm spaces, there are really two definitions here, and though these depend upon a vector space V over the real field and over the complex field respectively. Thus, when the underlying field is a real, then V is called a real inner product space. Otherwise, it is called a complex inner product space. In the real case, the axioms are same, except that the I1 will be written without the bar over a v comma u inner product of v comma u, since the complex conjugate has no effect over a real. When I1 is combined with the I3 and I2, we have the inner product of a u plus v comma w is equal to the inner product of a u comma w plus inner product of a v comma w. But now when we have a linearity in the second argument, that it is the inner product of a u comma lambda v is equal to be the conjugate over the lambda into the inner product of a u comma v. Thus, the inner product is linear in the first variable and conjugate linear in the second variable. As a consequence of this, we easily get that the inner product of a lambda u and mu v is equal to be lambda into the conjugate of a mu into the inner product of a u comma v for lambda mu belongs to a field f. And thus equal we shall use this formula often. In fact, we deduce the following general properties of the inner product, which are indeed immediate consequences of the axioms 1 to 4 of definition and can be verified easily. Here, 0 we denote the 0 vector in a V and 0 denotes the scalar 0 in a field F. Then for any vector V belongs to be a vector space V, we have a 0 dot V is equal to be the 0 vector. So that by the linearity property of the inner product, we have this. Given a vector space V over a field F, a semi-inner product for V is a function on V cross V, which satisfies all the axioms of an inner product except number 4. And instead of a I4, satisfies just the condition u inner product of a u comma u is positive. Thus, a semi-inner product allows the possibility for some u not equal to be 0, inner product of a u comma u is equal to be 0. For example, let V be the set of all sequences of u such that u1 is equal to be 0 for all but a finite number of values of n. For u and v is equal to be the sequence vn in this space v, define inner product of a uv is equal to be summation of u and conjugate over the v, then this defines a semi-inner product, but it is not a inner product. In an inner product space, we have for each uv w belongs to be v and alpha beta belongs to be f. Number one, inner product of 0 comma u is equal to be u inner product of u comma 0 is equal to be 0. Number two, inner product of a alpha u plus the beta v comma w is equal to be alpha times the inner product of a uw plus beta times the inner product of vw. This is the linearity property. And then we have a conjugate linearity will be there. The inner product of a u comma alpha v plus beta w is equal to be alpha conjugate of u inner product of a uv and beta conjugate and into the inner product of a u comma w. First one is very simple to prove it out. Inner product of a 0 and u can be written as a 0 dot 0 comma u, and 0 will come outside because we know that the lambda times u comma v is equal to be lambda times uv. So here it comes out as a scalar, so it is equal to be 0. Also we have a u inner product of u comma 0 is equal to be conjugate of 0 comma u, which is equal to be a conjugate of a 0, which is equal to be 0. And it is very by the property which is having a linearity property over the first argument. We have property number 2. Now we could discuss the third one. Inner product of a u comma alpha v plus beta w can be written as a conjugate of alpha v plus beta w comma u, which is equal to be the conjugate over the alpha vu plus the beta times the inner product of wu. And we know that the conjugate of a plus b is equal to be conjugate of a plus conjugate of b. So we have applied up here. And further, we're using the property out here, the alpha comes out, which is equal to be alpha times the conjugate of v comma u and the beta conjugate into the conjugate of w comma u. And using up of the property over the inner product, this is equal to be alpha conjugate inner product of a uv and beta conjugate inner product of a uw. And this can be extended to further in a general sense. It doesn't have any effect out there. So we have from these definitions we have say that the key properties that characterize the inner product are Hermitian symmetric, conjugate, bilinear, and positive definite. So now we discuss the Schwarz inequality. Okay. So we may observe that the dot product A dot B can be written up like this over the R cube, and the absolute value is equal to be A dot A power 1 by 2 in R cube. If V is an inner product space equipped with an inner product, the norm on a V associated with the inner product is the non-negative real number defined by the formula this into the inner product of a u comma u. Here it is clear that for every u belongs to be V and alpha belongs to be complex, we have the homogeneity condition, that is a norm of a alpha u square is equal to be inner product of a alpha u comma alpha u, which is equal to be alpha into the alpha conjugate into the inner product of a u comma u, which is equal to be modulus of a alpha square into the norm of u square. Hence norm of a u square is greater than or equal to 0 with the equality if and if only u is equal to 0. This property is called the positive condition of the norm. And for z is equal to be over the unitary space, the norm of z will be defined as square root of inner product of z comma z, like this. And this observation shows that the definition of inner product arises naturally as a generalization from the concept of Euclidean length that is familiar for the set of real or complex numbers. A question that naturally arises here, given an inner product on a vector space V, is the map defined here is a norm on V. So now to prove that this norm is equal to be the under root of so to prove this we use Schwarz inequality. If it is an inner product on a linear space V and x and y belongs to be a V, then modulus of inner product of a x comma y is less than equal to be norm of a x into norm of a y. The equality holds if and only if x and y are linearly dependent. The above result is obvious if y is equal to be 0, hence assume that y is non-zero. Then for alpha belongs to be a field f, we have norm of x minus alpha square is positive. Therefore, norm of x minus alpha whole square is equal to be inner product of x minus alpha y in comma x minus alpha y, which is equal to be norm of x square minus x comma alpha y minus inner product of alpha y comma x is equal to plus modulus of alpha square norm of y square. And using up a property of the inner product, that this becomes equal to be the conjugate of inner product of x comma alpha y, and again using up a property of x plus x conjugate is equal to be 2 times the real part of ax. We use that, so which is equal to be norm of ax square minus 2 times the real part of x comma alpha y plus modulus of alpha square over into the norm of y square. So by taking alpha is equal to be inner product of xy over the norm of y square, we have modulus of alpha square norm of y square is equal to be modulus of xy inner product square over norm of y square. And inner product of x comma alpha y is equal to be conjugate linear in a second argument, which is equal to be alpha bar xy inner product, which is equal to be this, so that we have 0 is less than equal to be norm of x minus alpha square, which is equal to be norm of x square minus of modulus of xy square over in norm of y square. Hence, we get the result. And if this is equal to be equality holds up, in that case, norm of x minus alpha y is equal to be 0. And in this case, x and y are linearly dependent. Also, if x and y are linearly dependent, then we have the given result holds up. Of xy is equal to be norm over x, norm over y. Yeah. So now we have got a relation out here that using a Cauchy-Schwarz inequality, that if x and y are in an inner product space, then the modulus of inner product of xy is equal to be the under root of the x comma x into the under root of inner product of y comma y. And if now we have a further theorem out there where the norm is being defined over the inner product, and we have to prove that this is a norm over the inner product. So say this is a linear space, and then x to be defined over the map will be here. Norm of x is equal to be under root of x comma x is the norm on x out there. So as this is the inner product on linear space x, so using the Schwarz inequality, we have a norm of x plus y whole square is less than equal to be norm of x plus norm of y whole square, and thus it satisfies that the norm of x y is less than equal to be norm x plus norm y. So it is easy to be satisfied the other properties. Here we have satisfied the triangle inequality. So hence inner product spaces are norm spaces and Hilbert spaces are Banach spaces. But not all the norm spaces are inner product spaces. So further, if x and y are two vector spaces in an inner product space, then the norm of x plus y whole square plus norm of x minus y square is equal to be 2 times the norm of x square plus 2 times the norm of y square. This property is known as the parallelogram law. The second one is the polarization identity, which is the 4 times the inner product of x y is equal to be norm of x plus y square minus norm of x minus y square plus iota norm of x plus iota y square minus iota norm of x minus iota y square. So now we get the proof of these identities. So let x and y are two vectors in an inner product space. So norm of x plus y square is equal to be inner product of x plus y, and using up a property of an inner product, we get this is equal to be norm of x square plus norm of y square plus inner product of x comma y plus inner product of y comma x. Similarly, norm of x minus y square can be written as the norm of x square plus norm of y square minus the inner product of xy minus inner product of y comma x out there. And further, we have going to be add up when we are going to be add up these two quantities, we will get up the required result. We get the first result is being proved when we add up these two parts. And second, we have to go with the polarization identity. We have on subtracting these two parts, we have a norm of x plus y square minus a norm of x minus y square is equal to be 2 times the inner product of x comma y plus 2 times the inner product of y comma x. And on replacing y with the iota y, we get the result will be replaced by this. And further multiplying both sides by iota, we get this part is there, and hence by adding up all these parts, we get this is equal to be 4 times the inner product of x comma y. Hence we get the result out. So now we are going to discuss the Hilbert space or inner product is jointly continuous. That is, the xn converges to be x, yn converges to be y, then inner product of x and yn converges to inner product of x comma y. It's simple to prove it out here. So we consider the modulus part of inner product of x and yn minus the inner product of x y, which is equal to be by adding and subtracting the inner product of x and y here, and using up the property of the inner product, these two terms are being combined up, and further these two terms are being combined here. This is xn minus x, we have yn minus y, and this is again we have xn minus x inner product out. And this would be further, we know that using up the modulus property or triangle inequality, we have this is less than equal to be this part plus this part out. And using up Cauchy-Schwarz inequality, this is less than equal to be norm of xn, norm of yn minus y. And further, we have already given that the xn converges to be x and the yn converges to be y. So this part converges to be y. This is xn converges to be x, converges to be 0. So we can say that this part converges to be 0 or epsilon. So we can say that the inner product of x and y and converges to be inner product of